Swayam Prabha. Digital India. Educated India.
Welcome to lecture 6. Today we are going to talk about the quotient ring and isomorphism theorem. So, we have already talked about, we already know about the structure of quotient group. What we have done there? We have started with a group and then we have considered a normal subgroup of that group, and then we have talked about the quotient, and then we have seen that on the set of left cosets by that normal subgroup, if I consider, then it also has a group structure, and that is what known as the quotient group. But then we can ask the same thing for the ring, whether if you start with the ring and then if you go take the say the left cosets of an ideal, then whether this set of left cosets has a ring structure or not. And if it we are able to give a ring structure on that, then we will call that ring to be the quotient ring, and we will try to investigate that what properties of that ideal we should have, so that we can talk about this quotient ring and all. So, let us start with the quotient ring. So, what I am trying to do is that, so let us start with an arbitrary ring R. So, let R be a ring and I is an ideal of R. So, since it is an ideal, it is already a subgroup with respect to addition, and I know that R is a has a group structure with respect to addition. It is in fact an abelian group. So, this subgroup is abelian. So, I can talk about the set of left cosets, and already this set of left cosets has a group structure that we know from the group theory. So, the thing that we like to define now, if we want to see whether this set of left cosets with respect to I has some ring structure or not, for that we need to define the multiplication on the set of all left cosets. So, if we want to do that, then what are the obstructions that we are facing? So, let me first write it down that since I is an ideal, therefore, since I is an ideal, so it is a subgroup of R, and since R is an abelian subgroup with respect to addition, therefore, this I is in fact a normal subgroup, because every subgroup will be a normal subgroup if you are in an abelian group. So, R is in fact a normal subgroup of R. So, then if I consider all the left cosets, then the set of all left cosets, the set of all left cosets that I denote by R quotient I has a group structure. So, what is this group structure? Group structure with respect to addition, right? Group structure with addition. How this addition is defined? With addition defined as, so I consider two left quotients from this set of left coset R quotient I. So, let 1 plus I is one left coset, another left coset say B plus I, and I would like to add these two left coset. How I am doing that? This is coming from the group theory, you already know this is nothing but A plus B plus I. This is how this addition of two left coset is defined. Now, the question is that whether we can define a ring structure on this set of left cosets. So, does R quotient I has a ring structure? So, if I want to see whether it has a ring structure or not, then I have to define the another binary operation, which is the multiplication operation. That means, I need to define the multiplication of two left coset. So, how do you define the multiplication of two left coset? So, let us see that if I try to define say A plus I is one left coset and I am trying to multiply it another left with it another left coset B plus I. So, how do I do? So, the natural way you can think of is that maybe A plus I dot B plus I have to use the multiplication operation on the ring, because we do not have any other operation. So, if I somehow want to use that, then the natural way will be that you multiply these two elements A and B and consider the left coset. So, now if I want to define in this way, then I have to check whether this definition is well defined or not. So, that means, so A plus any element of A plus I will be of this form, basically A plus U, and any element from B plus I can write it as B plus V, where these U and V are elements of I. So, now if I take the product as the distributive law over R, the multiplication operation in R, if I want to apply using the distributive property, what I can do? I can write this thing as A B plus A into V plus U into B plus U V. So, now you can see that if I consider, since I have started my I to be an ideal, therefore, this term A V also belongs to I as V belongs to I. This term U B is also in I, because U is in I, and of course, this term is in I. Therefore, these three terms, if I consider, this belongs to I. Therefore, this I can write it as A B plus I, some element from. So, this is an element of I. So, if I multiply this, then I am getting an element A B plus some element from I. So, here I have that U and V are element of I. So, now here you see that we need that I is an ideal. If I just want to replace I with a left ideal or right ideal, then it will not be useful, because if I just assume that I is a left ideal, then only it will be closed under left multiplication. So, that will imply that this element this AV will be in I, but it does not imply that UB is in I, because this B I am multiplying from the right hand side. So, if I consider that I is a left ideal, then this element will not be again in I, or if I simultaneously assume that I is an right ideal, then also it will be not in I. So, in that case I need my I to be an two sided ideal, which is nothing but an ideal. So, since I am assuming throughout that R is a commutative ring, so for us it is not making any difference, but if you are trying to do this thing in a non-commutative ring, then you have to be careful that you can talk about the quotient ring when you consider I to be a two sided ideal. Otherwise, this multiplication of two left coset is not in general defined. There are difficulty in doing that. Okay. So, now the next thing that I have to see that the way I have defined this multiplication is in fact a well defined operation. So, if I want to show that this multiplication is well defined, so how do I check the well definedness? So, that means why do I need to check the well definedness? Because these are left cosets. So, instead of I can represent the same left coset with two different representations. So, for example, a plus I suppose is same as the left coset a prime plus I, and b plus I denotes the same left coset as b prime plus I. Now, when I multiply, I will get a b plus I, and on the other hand I will get a prime b prime plus I, but that too should also be equal, right. So, in order to check well definedness, I need to check that if this happens, then I want to show that a b plus I will be equal to a prime b prime plus I. So, how to prove that? If I want to show that a b plus I is a prime b prime plus I, then I need to prove, basically I need to show that a b minus a prime b prime should be an element in I. So, now try to use the hypothesis. So, from this what I can write, these two left cosets are same. So, that means a minus a prime belongs to I. Therefore, I can write a minus a prime equal to u for some u in I. So, this implies that a is nothing but a prime plus u. Similarly, from this side I can get that b minus b prime is in I, which implies that b minus b prime is equal to v for some v in I. So, this implies that b is equal to nothing but b prime plus v. Now, if you multiply these two elements, what do you get? So, now this a b is nothing but a prime plus u into b prime plus v, which I can write it as a prime b prime plus a prime v plus u b prime plus u v. So, now again you can see that since I is an ideal, therefore, each of these elements that I have underlined here is in I. Therefore, this element is in I. So, this I can rewrite as a b minus a prime b prime belongs to I. So, this implies that this a b and this a prime b prime denotes the same left coset. So, I have defined a multiplication operation on the set of left cosets, and I have shown that this multiplication operation is well defined. So, if I want to show that with respect to this addition and multiplication operation, this set of left coset forms a ring, then there are two more things I need to check. One is that this multiplication is associative, that is a routine work. So, you can check that multiplication defined in. So, let me denote this equation where I have defined the multiplication. So, denote this equation. This is how I have defined the multiplication. So, let me denote this by star. So, now I am saying that if you define the multiplication of two left cosets in this way, then it is very straightforward to check that this multiplication defined in star is associative. So, this multiplication is associative, and what will be the multiplicative identity in this case? So, multiplicative identity will be nothing but the image of the identity element in the left cosets. So, that means, R quotient I has the multiplicative identity, the left coset corresponding to 1. So, 1 plus I, and the additive identity will be nothing but the corresponding left coset of 0, and additive identity is denoted by 0 plus I. So, that is in fact the ideal I itself, the additive identity. Therefore, we are able to prove that R quotient I is a ring with this addition operation and multiplication operation defined as previously, and this ring is known as the quotient ring, which is known as quotient ring. So, I have now defined what is a quotient ring. So, starting from a ring and starting with an ideal, I can talk about the set of all left cosets, and on the set of all left cosets I have seen I have addition operation and I have also multiplication operation, and with respect to these two operation it is in fact having a ring structure which is known as the quotient ring. So, now let us give you some example of quotient ring. So, let me start with some examples of quotient ring. So, the easiest example of quotient ring is Z quotient n z. So, here I know that Z is the ring of integers and n z is an ideal, and this Z quotient n z is nothing but the congruence modulo n, the congruence classes modulo n, and you know already the addition and multiplication operation defined on this one. So, this is a quotient ring of this ring of integers with respect to the ideal I as n z. So, we know that already this ring structure we have already studied, but in fact we can observe that this is nothing but the quotient ring in fact. So, now the next I will give you a non-trivial example. So, for example, if I consider suppose this polynomial ring over Z x go quotient by the ideal generated by this polynomial x square minus 2. So, I would like to understand that what will be the structure of this quotient ring. So, here how does the elements are look like, or how does the distinct quotients look like. So, the question is how does the distinct quotient look like in R. What is R? I am denoting this quotient ring by R. Okay. So, let us try to investigate how does it look like. So, we have what is the additive identity in this quotient ring R? The ideal 0 plus the ideal generated by x square minus 2. So, this x square minus 2, this element. So, the ideal I am writing as this by this notation, this bracket. So, this is nothing but the 0 element in this quotient ring. So, if these two left quotients are same because they are representing the same element. So, from here I can say that this x square in this quotient ring is same as the element 2 here in the quotient ring. So, then I whenever I am doing the operation in the quotient ring, I can replace always this x square with 2. So, that will simplify the left quotients. So, this will simplify the elements of the quotients. So, how does it simplify? So, let us see with an example that how does it this simplifies the structure. So, for example, if I consider suppose this following polynomial 7 x to the power 4 plus 5 x cube plus 3 x square plus 2 x plus 1. So, consider this element in the corresponding left quotient. So, let us look into the left coset corresponding to this element in the quotient ring. So, now in the quotient ring I know that x square is same as the element 2. So, wherever there will appear x square I will replace it with 2. So, then I can rewrite it as 7 x square plus 5 x square into x plus 3 x square plus 2 x plus 1 plus this ideal. So, this I can rewrite, I will replace everywhere x square with 2. So, this will give you nothing but 7 into 4 plus 5 into 2 plus 3 x square sorry will be replaced by 2. So, this 3 into 2 plus 2 x plus 1 plus this left coset. So, this is nothing but 28 plus 10 x plus 6 plus 2 x plus 1 this ideal. So, this I can simplify and this I can rewrite it as nothing but 12 x plus 35 plus x square minus 2. So, you can observe that whatever element, whatever polynomial I choose in Z x, and when I see it as an element in the quotient ring, then everywhere I am replacing x square with 2 and I am landing with a linear polynomial. So, that means every polynomial in the every element in this cosets will look like will be of the form a x plus b. So, thus every element will be of this form, this p x plus every element of this quotient ring will be of this form, where this is equivalent to a linear polynomial of the form a x plus b, because x square and all the higher order terms I will this x square can be replaced by 2. So, I will be left with only the linear term. So, I can rewrite any polynomial as I have shown you above in the polynomial of this form a x plus b. So, where these a and b are varying over integers. Now, you can ask that whether the elements of this form a x plus b are all distinct or not. So, suppose that these are not distinct. So, then what kind of implication does it give? So, question is, can these two elements can two of these elements are distinct. So, in order to check whether all these elements are distinct or not, so suppose they are not distinct. So, that means I am assuming that a x plus b, this coset is same as c x plus d. If that is the case, then I can rewrite it as nothing but a minus c x plus b minus d. This element belongs to the ideal generated by x square minus 2. But this is a linear polynomial. So, it cannot be in the ideal generated by x square minus 2, because any element in this ideal generated by x square minus 2 will be a multiple of x square minus 2. So, its degree should be greater than equal to 2. So, that means it forces me that this polynomial has to be the 0 polynomial. So, this implies that a minus c into x plus b minus d has to be the 0 polynomial. So, that means that a has to be equal to c and b has to be equal to d. So, that means if these two cosets are same, that means they are actually the same elements. That means all the elements of the form a x plus b, they are all distinct. Thus, the elements of this quotient ring are of the form a x plus b, this left coset, where each of them are distinct. So, I have shown you that how does the elements of this quotient ring looks like. So, if you just see into the structure, then you can observe that this is basically nothing but the remainders we are getting. So, if you divide any polynomial by x square minus 2, then whatever the remainders you are getting, that is nothing but the elements of this quotient ring. So, that is what the observation is. Now, another example that I would like to say is the following. So, consider this ring R to be nothing but Z I quotient 3 plus I. So, before proceeding further, let me denote what this Z I is. So, this Z I is nothing but the elements of the form A plus I B, where A and B are varying over Z. So, this is, you can see that addition is nothing but the addition of complex numbers, and the multiplication is also defined in the same way as the multiplication as complex numbers, and this is in fact a ring. So, this is a ring known as the ring of Gaussian integers. In fact, it is a subring of the ring of complex numbers. In fact, Z I is a subring of C. So, this is the ring of Gaussian integers. This is a very important ring. If you study number theory, then it has many applications in number theory. So, this is the ring that I am considering, and the ideal here I am considering is the ideal generated by 3 plus I, and I am interested in understanding how the elements of the left cossets, how the elements of the quotient ring look like. So, in the quotient what is happening, this 3 plus I, this element is nothing but the 0 element. So, this is same as 0 element. So, if that is the case, then it from here I can say that I in the quotient ring is nothing but the same as the element minus 3. So, here in the quotient I can replace I with minus 3. However, also I have another relation, also we have that, we know that I square is equal to minus 1. So, if I square this previous equation, then what do I get? So, squaring equation 1, we can write that this is nothing but minus 1, the left this quotient corresponding to minus 1 is same as the quotient corresponding to 9. So, this implies that this is nothing but this 10, the element corresponding to this 10 in the quotient is same as the 0 element. That says what? That says that every coset can be, I can if every coset in this I can rewrite it as where I can replace my I with minus 3. So, let me just write it quickly. So, every coset can be written as A plus I B and then 3 plus I, this ideal, by replacing I with minus 3 by, and not only just replacing I with minus 3, and I am also having, whenever I am having 10, this is equivalent to 0. So, 10 with 0. So, therefore, every coset is of the form. So, this whole thing I am now completely, this whole thing, this wherever this I is appearing, I am replacing it with minus 3, and whenever 10 is appearing, I am replacing with 0. So, this whole thing I can rewrite it as sum is of the form C plus this left coset, where C is an element in the modulo class Z. So, that means what I am getting is that this is in some sense this Z I quotient 3 plus I, this quotient ring is in fact isomorphic with Z 10. That is what I will be proving next time, but this gives you an intuition of how I am visualizing the elements of this left coset as element of Z 10, that I have shown you here, because here you can see that every element this left coset where this I is replaced with minus 3 and this 10 with replaced with 0. Therefore, they are of the form C plus 3 I, and here here C is nothing but coming from the 10 modulus Z. So, congruence this 10 has C has only these choices that it can come from Z 10. But in the next time I will show you exactly how this isomorphism is coming, and today I will finish with this one. And so, these are the references for today's lecture. Thank you.